Welcome back to another video. So, have you ever really stopped to wonder why certain rules of the universe seem to be completely unbreakable? I mean, we're all taught that energy can't be created or destroyed, right? Or that an object in motion stays in motion. But why? These aren't just some random regulations from a cosmic rulebook. Turns out, they are deep, fundamental truths about how everything works. And the answer, believe it or not, comes down to a single, unbelievably beautiful idea that connects everything.
To crack this mystery, we first have to take a word we all think we know, symmetry, and look at it in a completely new way. This is the key that unlocks the whole thing.
Okay, so when you or I hear the word symmetry, we probably picture something like a butterfly's wings, visually balanced, perfect mirror image. But for a physicist, the definition is way, way more powerful. It means a system stays the same even after you do something to it. It has what's called invariance under transformation. Let me give you a great analogy. Imagine a perfectly smooth sphere. No marks, no scratches, nothing. Now, if you close your eyes and I give it a little spin, when you open them again, you would have absolutely no way of knowing it moved. The sphere looks exactly the same after being rotated. That's symmetry. So the big idea here is some changes don't actually change anything at all.
And this brings us to an absolute giant of mathematics, Emmy Noether. Back in 1915, she had this totally revolutionary insight. She realized this idea of symmetry wasn't just for objects. It was about the fundamental laws of physics themselves.
And this is her masterpiece, Noether's theorem. It says that for every continuous symmetry you can find in the laws of physics, there must be a corresponding conservation law. It's not a suggestion, it's a necessity. This is the master key, the direct, unbreakable link between symmetry and the fundamental rules of our universe.
So how did she even prove this? Well, her work is built on something called the principle of least action. And a really simple way to think about it is that nature is, kind of lazy. It's incredibly efficient. A system will always choose the path that takes the least amount of action. Noether showed that if a system has symmetry, this natural laziness forces something to be conserved. It's just how it has to be.
Okay, so that's the theory. But how does this amazing theorem actually affect us in the real world? Let's take a look at the big three symmetries that govern pretty much everything we experience.
First up is symmetry in time. This just means the laws of physics don't change from one moment to the next. If you drop a ball today, it's going to fall the exact same way it would have a billion years ago. The rules are always the same.
And because the laws of physics are symmetrical across time, Noether's theorem guarantees that energy must be conserved. The reason energy can't be created or destroyed is because the universe doesn't just change its rules on a whim. It's incredible.
All right, symmetry number 2 is all about location. The laws of physics are the same everywhere. An experiment will give you the same result whether you do it in Vellore, Mangalore, or on the far side of the Andromeda galaxy. Space is uniform.
And what law does this symmetry give us? The conservation of linear momentum. Yep, the idea that an object in motion stays in motion exists because there's no special preferred place in the universe. It's the uniformity of space that forces momentum to be conserved.
And that brings us to the third big one, rotational symmetry. The universe doesn't have a favorite direction. There is no fundamental up or down. The laws of physics work the same, no matter which way you're pointing. This symmetry is what gives us the conservation of angular momentum. It explains why planets keep spinning in orbit and why an ice skater spins faster when she pulls her arms in. It all boils down to the simple fact that direction doesn't matter in the grand scheme of things. So let's just recap, because this is the really powerful part. You have this perfect one-to-one relationship. Symmetry in time gives you conservation of energy. Symmetry in position gives you conservation of linear momentum. And symmetry in rotation gives you conservation of angular momentum. It's not luck, it's not a coincidence, it's a direct consequence of the shape of our universe.
But, a theorem this earth-shattering didn't just pop into existence. We really need to talk for a moment about the incredible mind who figured all this out, Emmy Noether.
I mean, just listen to this quote from Albert Einstein. He called her the most significant, creative, mathematical genius since women began receiving higher education. And this was at a time when she was facing enormous obstacles as a woman in academia. Her work was just so powerful, it completely reshaped modern physics. In fact, she even saved Einstein's own theory. When he came up with general relativity, he hit a huge snag. It looked like energy wasn't conserved in a universe with curved spacetime.
It was a massive problem. But it was Noether who applied her theorem to the puzzle and showed exactly how conservation works on a cosmic scale. She solved the paradox and helped solidify one of the greatest scientific theories ever.
So what is the big takeaway here? I think it's this. The universe isn't really running on a list of rules. It's running on a series of fundamental balances. Because the very stage of the universe, space and time, is fair and symmetrical, all the actors on that stage, all the matter and energy, have to obey these conservation laws to keep everything in perfect balance.
And this leaves us with a final, really fascinating thought. Noether's theorem shows us that symmetry leads to the stability and predictability that makes our universe work. But what happens when a symmetry is broken? Well, that question is what leads us into some of the most exciting and cutting-edge areas of modern physics today. See you again tomorrow.